So we have this ring here, which is maintained in equilibrium by a cable AB and CD. So here is AB, TAB, and a cable CD to TCD. We have a 300-pound block, which will be a force. The spring constant of GJ is 900. It is also known that the spring HG is extended 0.2 and spring GJ is 0.5 feet, respectively. And we know that the cable CD is known to carry 200 pounds. So I'll put 200 right here. So we know a lot of information about the forces acting on this ring right here. I'll start with my two springs. So these two springs are in series. So I remember everything I know about series springs. And one of the things I know is that the forces in these two springs have to equal. And we can see why if we just do a quick free body diagram on this purple point here. There's only two forces acting on this purple point. One is the force from HG, the other is the force from GJ, and therefore these two forces must be equal and opposite for there to be balance, for this purple point not to move. So I can use that fact. Remember, the force in a spring is K times X. They tell me that the spring HG is extended 0.2 feet, and that spring GJ is stretched 0.5 feet. And I also know that stiffness, that K value for GJ. So I know the K and the X. That's enough to calculate our force in that GJ spring. I'll just get 450 pounds. And of course that implies that the force in the HG spring must also equal that 450 pounds. Remember, this is all about knowing exactly how springs in series and parallel work. There's a lot more details than just knowing, those K equations and stuff like that. So I have a video on that if you want the full story on springs in series and parallel. So I know this force acting on our purple ring, this force. I know the spring force acting on our purple ring, that 450 that I just found. Let me just make the free body diagram for that purple ring. So notice that my only two unknowns are TP, that's the tension going into our pulley system here, and TAB. We know all of our other forces. And since we only have two unknowns, and we have two equations to solve, that means we have enough information to figure out what these unknowns are. That's great. But it leads me to believe that this problem was not designed correctly. Let's say we figured out what that TP was. We would know the tension, and basically we'd be able to figure out the tension in this entire pulley system. And that tension better work itself out so that it perfectly equals to 2,600 pounds going downwards. I don't think it will. I think that the person who made this problem wanted us to start here first. Wanted us to, work through this pulley system, figure out T this way, and then use that to figure out the force in the springs. I think the designer of this problem forgot that forces of springs in series are equal to each other. So I think this problem is just a bad problem. It's sort of conflicting itself. So I'll just continue with this, with how I'm doing it. And I just bet you that we're not going to get a nice balance when we look at the FBD for this 2,600 pound block. So here I am summing up my forces in the X direction. Just take a moment and make sure you're okay with that. And here's my sum of the forces in the Y. So I can solve this equation for TAB here, not a problem. I'll just crunch that math. And I'll get 323.8 pounds. So we got that answer. Of course, I can take that, plug it in right here for TAB in this equation, and figure out what this tension is here, leading into our pulley system. And that's just another bunch of math calculations on the calculator. And we'll get 132.8 pounds. So there's our part A done, and our part B done as well. Before I do part C, let me just do that check like I was talking about earlier. Let me just do the pulley system analysis and see if it all agrees with each other rather than, contradicting itself. So let me dive into that pulley system. So I'll just call this T here, even though I know exactly what it is. So this rope right here is all at T. If I do a quick FBD on this pulley right here, I have 2 T's pulling it up, which means I also need to have 2T pulling it down as well. So we got 2T right there. Alright, so I'm going to keep following that purple rope. Looks like it terminates on this nail right here. Let's do a quick free body diagram on this pulley right here. Now this actually really confuses me because if I take a look at this pulley, it actually has this T pulling it to the left. And I don't see any other forces pulling this to the right that balance that leftwards T force. So that's really confusing. I guess I'll just ignore that. Well, I do have 2 of our T's going down that same purple rope. Therefore, this green rope must be 2T. So I'll write 2T. And I'll follow that green rope, Quick FBD on this pulley. 2 of those green ropes going up. So each of those green ropes is a 2T, which means this rope pulling down must be a 4T. So 4T. Alright, I'm still following this green rope here. Okay, so it looks like I have 3 green ropes pulling this pulley down, and each of those green ropes is 2T, which makes this yellow rope 6T. So 6T, tracking that 6T, 6T. And I'll stop right there because I'm going to take a look at this pulley. I have 2 of those yellow ropes going up, 2 of those 6Ts going up, which means I have to have a 12T going down. So all in all, looking at that block, we have a 2T going up on the left, a 4T going up in the middle, and that 12T blue rope going up. And of course, the force of the weight is that 2,600. I can do a quick Newton's second law. 2T going up, 4T going up, 12T going up, minus 2,600 must equal 0. We can easily solve for that T. Let's see what the math tells us. Is 144.4 repeating pounds. And that obviously is not the same T that we got when we were analyzing just this system by itself. So, yeah, we just proved that this problem is not well designed. And also, I didn't really like how this pulley here had that rope coming off to the left. I mean, we need something to fight that to the right. I mean, that's two things I really don't like about this problem. So I will just box this equation up and put over there to the right, just so you have it. But as we move on, I will just use that value right there. Okay, spring constant of Hg. So let's go back to those springs again. So remember, the problem explicitly tells us that Gj is a stiffness of 900 and a stretch of a half, which yields a force of 450. Because these two springs are in series, I know that Hg has that same amount of force going in it. So knowing that this is 450 and the stretch in Hg is 0.2, now that is given by the problem, we can actually solve for this. So I can do 450 divided by 0.2, and I'll get that K as 2250 pounds over feet. And our final part, the components of DC, force DC, I presume, along line AB and EF. So here's our DC force, and let's say here is our AB force of 323.8, and DC is 200. So they want this right here. This is the component of the 200 that's in the direction of force AB, and this is the other component of our DC force that is perpendicular to the TAB direction. So again, they want this, the component of DC along line AB. So just remember dot product. We can use dot product to do this. They're essentially asking for, or another way to phrase what they're asking for is project force DC in the direction of AB. And actually, now that I'm thinking of it, we don't even need to use dot product here because we have this angle. The angle in between CD and AB is going to be this 50. So we can just do the hypotenuse, this guy, times the cosine of 50 to find this adjacent side right here. Easy as that. So the tension DC component along AB will equal the hypotenuse, 200, times the cosine of 50, and of course we can calculate this as 128.6 pounds. So again, that's the length of this adjacent line right here, the component of TDC in the direction of AB. Now we can carry out a very similar process for the component of DC that is in the direction of EF. Pretty much the exact same process. Here's DC again with that magnitude of 200. I'll just draw a horizontal line. Here's our angle of 30. Here is that downwards force of 300. Since we have a 90-degree angle here, that means that this angle right here must be 60. So let me break this vector down into components. Here's one that's in the direction of that EF line, and I'm going to tip to tail at it. Here's the other one that is perpendicular to that EF line. So 200 times the cosine of 60 should do it for us to grab that adjacent side. So hypotenuse times the cosine of 60, and that'll get for us 100 pounds. So that is it. We've answered all the questions. Now just watch out for this problem and other problems like it. Fundamentally speaking, there's two ways to calculate this tension, and that's a big problem. You can calculate it by starting here and working through the Pulley system to find T, or you can figure out this by doing the free body diagram and some forces in X and Y on this ring. Usually there's only one way to calculate the solve for an unknown. If there's two ways to solve for it, they better darn well get you the same number, but usually I found that they don't, and it's a teacher mistake. So just watch out for those. Alright, feel free to ask me any questions on this problem.